say we're given a square matrix A and another square matrix B, and both are n by n, and suppose that we know that A times B is the identity matrix. Can we conclude? So can we conclude that B is equal to the inverse of A? Well, if we just go by the definition, the answer is no, because we also need that B times A is the identity matrix. Luckily, it turns out that since we're dealing with square matrices, we actually only need to check this one condition. Alternatively, we can just check this condition. And the reason is a theorem. Let A and B be square matrices of the same size. If either AB equals the identity matrix or BA equals the identity matrix, then A is invertible and B is A inverse. In other words, if either this condition or this condition, if one of those two conditions are true, then so is the other one. Let's prove this. Proof. I'm just going to prove, so I'm just going to prove that BA equals the identity implies AB is the identity. Doing the other direction, that AB is the identity implies BA is the identity, is similar. Suppose that BA is the identity. Consider the system, or the matrix equation, AX equals 0. Multiplying it on the left both sides by B, we get this system of equations BA times X equals B times the 0 vector, or equivalently, using the fact that B times A is the identity matrix, this is X equals 0. So in other words, the system AX equals 0 has only the trivial solution. Then, by Tim, A is invertible. So all that's left to do is to show that B is indeed the inverse of A. We already know that A has an inverse, so we just need to show B is that inverse. Well, let's see if we can do that. We have B equals B times the identity matrix, but by definition of the inverse matrix, the identity is A times A inverse. But this guy here that I just put in parentheses, we are assuming that it's the identity. So therefore, this is I times A inverse, or in other words, A inverse. So this string of equalities tells us that B is equal to A inverse, and we are done. Tombstone.